equator would be in the sky. There are various other kinds of lines that you can draw up in the sky there. And what we're concerned about in what the Rambam is discussing is a very, very special line. And in order to illustrate that, let's see, I don't know if that's enough room over there. We're going to use this nice yellow ribbon. Now, do I have a volunteer here who wants to be the holder of this ribbon?
I'll do it.
Huh? Okay, great. What is your name? Huh?
Yeah.
Okay, Mr. Woody. Okay, yes, let's give him a big hand, everybody. Now I need a second volunteer. Who's the second volunteer going to be?
Well,
Excuse me, I'm going to have to ask you to move in here. Okay. Okay. Tully, from now on you're going to be, we're going to call you Shimshon because you're going to represent the sun for the time being, okay? Now, what happens in the sky is, I said that everything rises in the east and it sets in the west. And you have this thing going on with the celestial equator that we talked about and all that kind of stuff. And basically what happens is, in addition to all these things being painted on the inside of this ball up there, we have things like the sun and the moon. They themselves move around like little bugs crawling along the inside of this celestial sphere. They move around like little bugs. Now, our sun, what was your name again? Okay, Shimshon. Okay, yeah. I wanted to ask you to move around and try to count how many steps it takes you to go around a complete circle. You'll have to adjust the length of that thing to get a complete circle to walk around here. Walk around here. You have to move in a little bit over this way so that he has got enough room to move. All right, now, yeah, then you can just shorten this up. Just hold it right around. That's good. Okay, don't get me tangled up there. All right, now you see this guy walking around with a string. You might think he feels kind of silly, he probably does. But what is he representing here? He's representing walking around at a constant rate around the circle. Okay, how many steps does it take you to get around there?
25.
Huh?
25.
25, all right. 25. So we can sort of divide up this circle that he just walked around into 25 equal steps. Now I'm going to ask you to walk around again. I don't want you to get too dizzy, but you can walk around even a little bit faster.
Count?
And yeah, and I want that to be the starting point over there, this way over here. I want you now to take the end of this string, and I want it to sort of come up to a high point right over here. And then as it comes down over here, back down to the level where you're at there. And when you go over there to make it go to a low point over there. Now let's try that again. Go ahead. So let's go 1, 2, 3, 4. He goes very, very high. 5, and he comes he comes back to the center point again. And all the while he's walking around at a constant rate. He's taking his 25 steps, and now it's very, very low over there, cutting off those guys. Yeah, don't injure anybody. But I'm sure it is back to the middle point there after 25 steps. Took him about 25 seconds, let's say, okay? A step a second times 25 steps gets you all the way around the circle. This reminds me of a famous thing I learned in math a long time ago when I was a kid. And it's called rate times time equals distance. You ever heard of that one? If you go 30 miles an hour, that's your rate. And you go for 2 hours, that's your time. How far have you gone? 60 miles. Rate times the time is equal to distance, right? He's taking a step a second. If he goes for 10 seconds, he's taking 10 steps, right? Very, very difficult math. That is the essence of the beauty of the way the Rambam describes a very, very complicated thing, is that you always have to remember if you have something that goes at a constant rate, and you know how much time has elapsed in this constant rate, then you will know how far he has gone. Once you know where he starts, then you'll know where he is in the future time.
You know how fast he's going.
Huh?
You know how fast it has.
You know, that's your rate. You know how fast you're going. You know how much time has gone by. You know how far he's gone. Where is he? You must know where he started. If you know where he started, you add where he started, to how far he's gone, and you know where he is. Okay? Very important point. The entire basis of all the math that's done in Kiddush Hachodesh is based on this concept there. So he's taking one step a second around the circle. Now, obviously, we can't measure where stars are on the celestial sphere by how many steps he's taken. We have to measure it by some other means. But let's have you walk around just one more time. I know it's getting kind of boring. Let's just do the same thing and have the thing go way up in the sky high. Come back down to midpoint over here again. Sun going around the Earth, okay? Now we're going to do the same exercise again. Here we have our Earth. Here's California. Up until now, poor Yugi has been Earth. Now we're going to replace him, pretend that he is the Earth here. Okay, here's California. California, by the way, is the same height called latitude on the Earth as Earthstroke, which is where the Rambam is talking about all this stuff happening. So now, if we have the sun here, and I'm just so that you don't get bored out there, I'm going to give you an artificial sun called a flashlight. Okay? Can you catch this here? The tight ribbon is at any particular time, it will shine on the Earth at a particular place. Okay? If it's shining right there, at a particular point, at that particular point. Now let's take your little trip around the block again. And notice that he's going to start going up. All right? You don't even need the string anymore because we all get the idea of it. But as he goes way up, we see that the sun is now shining on the north part of the world. Okay? This is the summer. Wait, get back there. The sun is shining on the north part of the world over here. Now, as he continues in his trip around the world, and it comes back down to over here where he's even again, the sun will be shining on the equator of the world, the middle. He continues around, goes down, the sun goes way down, and the sun starts shining. This, the first day of spring. It's called in English a lot of different terms. The first day of spring, it's called the vernal equinox. Because at that point, day and night has equal 12 hours of the world round. And it's called Tkufas Nisan in Halacha. The actual Tkufas Nisan is that first moment when the sun is even with the equator, like this. And then the sun travels like a little bug on the inside of this big round thing, and it slowly moves its way up this way, climbing. You can do it again, it's great. Climbing until it's about 23 degrees. Where'd that word come from? We'll talk about degrees in a second. Stop right there, get back over here. Okay, until it's shining on the north part of the world. North part of the world, okay. Shining in the north part of the world, and if you look on the globes, you'll see a dotted line there called Tropic of Cancer. Now, cancer is unfortunately a terrible disease, and we don't even mention its name as a disease, but the real name for cancer means, what do you call it, a crab. And this is what we call Tkufas Tammuz. This is 90 days or so after Tkufas Nisan, the beginning of the first day of spring. This is the first day of summer, June 21st. This is the longest day of the year for the people who live in the north. Because the sun is above the horizon. It's so far north, the sun shines and we see around the curvature of the earth the sun for a long period of time. In the south part of the world, it's very cold because the sun is shining in the north part of the world. This Tkufas Tammuz, as I said, it has to do with, it's called the Tropic of Cancer. The sun is right above the Tropic of Cancer. Now let's come back around over here. Tishrei. First day of autumn, equal day, equal night, all the way around the world, 12 hours of daylight, 12 hours of night. You look on the Shabbos calendar, you see Shabbos starts around 6 o'clock in the evening, and then as the sun keeps moving along down there, it will go down to highlight the lower part of the world, lower part of the world, okay, lower part of the world, down, lighting up the lower part of the world, and it's right above a line on the globe called the Tropic of Capricorn. Capricorn is a name for goat. Is okay. Then the sun keeps moving along until it finally gets even again with the equator back to Tkufas Nisan. Okay, you boys I'm sorry, sorry, Mr. Shimshon, yeah, whatever, I'm sorry, I keep on forgetting your names. Anyway, you get to be my age, that's what happens to you. Okay, now, and we measured his progress around the world as 25 steps. There's a better way and a more uniform way of measuring things along this big inside of a ball that the sky looks like to us when we are inside of everything. What is that measure? That is a measure of degrees. Now, degrees is just a way of dividing up angles. Does everybody know what angles are? Your finger go out at an angle, right? Okay, angles. Doesn't matter how long your fingers are. What matters is the separation that they are here. That's the angles, okay? Angles, we define a 360 degrees as being going around the whole circle, like that. There's a measuring device for angles. That is a protractor, which you can buy in 99-cent store for 99 cents. This protractor is what you use for drawing angles. Basically, there's a little hole in it, and you can stick a pencil in there and make a dot. And then there's a line along there. And then written 0 this way. Well, as soon as he gets to 90 degrees, he's out there, then he's at Kufas Tammuz. As soon as he goes another 90 degrees, he's at 180 degrees, he's out here, he's at Kufas. Goes another, yeah, goes another 90 degrees. No, my protractor only goes this way, so I'll flip it over like that. Another 90 degrees, he's over here for the first day of winter, Teves, until he's back to 0 over there. 0. What's 0? 0 is a particular direction in space. Now I'm going to invent for you an amazing device. I just had the idea of it before I came here. I had about 3 minutes to invent this device. Now I'm going to build this device for you. All right. I have here 2 number 2 pencils. You can buy them at 99-cent store for hopefully a lot less than 99 cents. I also have here a paper clip. If I can get it off on the shirt. Hole there. Oops. No. I'm going to unfold this paper clip and proceed to see if I can stick it through these 2 erasers. I think I can do that. Yeah. That one worked. Okay. I'm going to stick through this one. Hopefully not through my finger also. Okay, gentlemen, you're about to witness a major moment. Okay. Now, as I said, my protractor has a convenient little hole in it. And I'm going to stick the end of this paper clip through this hole. That. Now I have just invented this wonderful device which will allow me to measure the angles between 2 things by simply sighting along one pencil. So if I sight along a pencil at U, for instance, and I sight along another pencil at U, then I can look on my protractor, measure the angle, and it is 70 degrees. Now this weird old device that I just invented, actually I didn't really invent because other people before me have invented much better ones that have like tubes with maybe lenses and telescopes in them so that you can look at a star up in the sky like that. You look at another star and say, oh, the angle between those stars is blah, 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 whatever it might be. This is while you're sitting out there in your nice comfortable chair in a nice warm sweater looking up at the sky, you have one of these devices, the real kind, which contains 2 things to be able to sight along one direction, and a measuring device to measure the angle with them. That's all you need to map the sky. Doesn't matter how far out the stars are, doesn't matter. It's just as if we're inside of a ball. Look one direction, another direction, measure the angles. The angles is all that the Rambam is talking about in Hilchos Kiddush Hachodesh when it's determining how things work. So, now I can tell you that it took him 25 steps to go around 25 seconds around this room, right? However, the sun in reality takes about 365.25 days to go around, right? and there's various aspects of halacha dealing with 365 days and 365.25 days. If you really measure it real carefully, we find our 0 spot over there, which I call Reish Nozzle Tleb. And I put this, one of my pencils pointing to that direction there, and I measure every day where the sun is. But wait a second, you're going to all say to me, how can you measure where the sun is? You can't see any stars where the sun is, right? Oh, so what you got to do is you got to be a little bit smart. You got to figure out at night where the sun is by measuring other things that you know are in relationship with the sun. For instance, you could, just after the sun goes down, say, oh, the sun just went down there. I can see a star. I'm going to point my first pencil or telescope down there, and I'll find another star up here and measure that angle. And that way you can measure the sun as it goes through its path. And there's various ways you can do that. Anyway, 365 days is a year, right? 365 and a quarter days. What happens when the sun goes around a full circle? How many degrees has it gone? 360. Now those numbers are very close to each other. 360, 365. So we can come to the conclusion that the sun moves a little bit less than a degree a day around the scope of the sky. So we have this big celestial sphere, this big inside of a ball that we are sitting in. Every single day, the sun is moving like a little bug, 1 degree a day. Next day, so it moves all the way up here, high up to shine on the northern hemisphere after about 90 days. Another 90 days back down, shines evening, 90 days down, back it up. Sun moves about a degree a day. If I know how fast the sun moves, and if I know where the sun starts off, well, I say the sun starts off at 0, because I decided that's where 0 is. 0 over there, that's where the sun is on the first day of spring. You tell me what day it is, I'll tell you where the sun is, because I know rate times time equals distance, and I know where it started. You tell me what day it is, I'll tell you where the sun is. That's very nice. There's only a slight problem. The slight problem is that the sun sort of speeds up and slows down. So it doesn't really move at an exactly constant speed. It doesn't move 1 degree a day, or just a little bit less than 1 degree a day. It sort of speeds up and slows down. That's because, as we now know, the sun moves in what's called an ellipse. You know, an ellipse is a squashed circle. It's got certain special characteristics. The ellipse that the sun moves in, the way that the gravitational attraction of the sun and the earth and all the planets is, what makes the sun sort of speed up at one part of its orbit and slow down at the other. When it's very far away from the earth, it appears to be slowing down. And it sort of like whips around close. It's a very, very slight difference, but it's a difference that needs to be accounted for in the calculations that ensue. Now, just as a very quick digression, basically what you do in all this kind of stuff is you start off with a very rough estimate of how things work. If I tell you that the sun moves a degree a day, that's pretty good for most purposes of life. You can figure out, if I tell you, well, it's 180 degrees since the first day of spring, you'll say, oh, it must be just about the first day of autumn. If I tell you it's, let's say, 18 days since the first day of spring, well, then you can figure out basically how many degrees the sun's moved, about a little bit less than 18 degrees, and it's sort of on its way up this way. As you need to know more and be more exact, because your measurements require more exactness, then you have to start taking into account other aspects of the thing, namely the fact that the sun speeds up and slows down.
It actually goes faster. It's because it's further away, so it looks like it's going slower.
Well, as far as we're concerned, it doesn't matter, because we don't. In reality, it does both. It changes its speed and it's getting further away. But as far as we're concerned, we are sitting in our chair outside, hopefully with a very warm sweater by now. And as far as we're concerned, all we care about is where the angular distance is from where it started. We use this idiotic device that I invented here and measure the angles. And you'll see, after you measure it day after day, and the way that people did, the way that Rambam did, or the way that other astronomers have done, you'll see that the sun speeds up and slows down. So, it turns out And that book that I showed you there, he talks about the actual formulas for how the sun speeds up and slows down. Very, very complicated mathematics. It's a discipline they call spherical trigonometry. And it's not easy to explain the mathematics of how it speeds up and slows down.
The Rambam speaks about it?
So the Rambam, first of all, has a Hakdama for this entire thing that the Rambam discusses, and that he says, you might think that I'm not being very exact. And he says, and you're right, I'm not being very exact. Because my only purpose in setting down all these calculations is to teach you whether or not the Levana will be visible on the evening of the 29th day of a month. That's all my purpose is for doing so. So therefore, I'm making certain approximations. What the Rambam has done is he's done this. Really, it's an amazing thing. The more you know about the subject, to see how brilliant what the Rambam did was he took calculations which are fairly complex, fairly difficult, and he simplified them so it becomes basically a cookbook. It's like a recipe. Take one egg, do this, put these things together, see what you get from here, use that, start over here, put this here. And as a matter of fact, if you're familiar with programming computers, or whatever, it's very, very closely associated with what a computer program, the essence of a computer program. Take one number, do something to it. Take another. If it's this size, then do this with it, do this size. It's a step-by-step process. We're taking very complicated calculations with the sun speeding up and slowing down, and I'm going to explain how to do it. How does he do it? I'll tell you, he does a very, very interesting thing. Now we had our sun going around with this ribbon, one step a second, at his constant speed, right? And we had our die-hard Earthman over here standing in the center. Now, when he's standing in the center, and he's measuring with my device here, he will find every day the sun moves at the same speed. And the Rambam says, let's start with the sun moving at the same speed every single day. And sure enough, the sun moves at the same speed. Now, if he were not standing in the exact center of where the circle was, but the sun was still moving at a constant speed around a circle, he would then see the sun appear to speed up and slow down using this device. Why? All right, where's our sun? Okay, thank you. All right, let's start going around again at your 25 steps, 1 step per minute thing, okay? Now, instead of let's have what's this little device here? I will notice that you're taking steps, and But yeah, start 1 step. Oh, 1 step. There's 1 step. It's a pretty wide angle there. I'm not going to bother measuring it, but it's a pretty, let's call it pretty wide angle, exactly 0.0 degrees. Okay. Now, if he's way over there, let's say, and let's say that I'm not in the center of the circle anymore. We're not in the center. You're a little bit farther off. He takes 1 step. That's a little bit less of an angle because I'm farther away from where he is. He goes 1 step. Let's make it really exaggerated. Go to the very end of the room there. Okay. All right. Now, so now you're way over there, and I'm going to point this thing right at you right now. Okay, and you take 1 step. Okay. Now I got a very small angle because he's so far away. Because my center of my circle is not in the center anymore. Where I'm looking at is not the center of the circle, even though he's got the same size steps, the same rate. Since each of those steps over there, did you drop my flashlight? since my observing of his steps, even though he's doing the same thing he did before, what is going to happen? Is he going to be faster or slower over there? Slower. He's going to be slower, right? Because every time he takes a step, he only moves this much. So he's only moving 1 degree. It doesn't look like 1 degree a day anymore. It looks like a smaller amount per day. So the sun is slowed down, even though he didn't slow down. But for me, it looks like he's slowed down. So putting our Earth guy outside the center of the circle, displaced from the center of the circle, has made the measurement of this more accurate. What the distance that he is now from the difference where he is from the center of the circle to this part, the Rambam talks about, that is called what they call the Gova HaShemesh. Gova HaShemesh is the amount displaced that he is, and the angle of the biggest part of the circle to where our 0 point is. Anyway, that's the that in a nutshell is a little bit explanation of how the orbits of these things work. Now, you notice that I told this gentleman to walk around with this ribbon and to lift it up and get over here and down here, and what happens, we see that this gave rise to how the seasons work, right? Now, this path that he took, and here, you don't have to be way out there anymore, you can go back into low Earth orbit. So this path that he took going up like this, I got it wrong. He went up like this, down, and up. It's actually a circle in and of itself. That circle is called, in English, the ecliptic.
What was it?
Is on a plane like this. It's going up like this. Right? Huh? That circle is inclined at an angle of 23.5 degrees to the equator. That circle is called the ecliptic. Huh? What? Here, if you look at this nice map of the sky that I'm going to leave you guys. The equator is over here. And this is the way it looks really right now. I printed this out. Actually, it's the way it looked about half an hour ago. But it's pretty close. Which way is north again?
North is that way.
North is that way. All right, so north is that way. So this basically is how it looks up here. If you were to go outside in that nice chair, you'd see the equator is over there. You wouldn't see it because nobody bothered to paint it on the sky. But the ecliptic would be sort of a line like this, and it intersects and it goes right through the equator. And that's the path of the sun. It turns out the planets, the moon, all seem to move along the ecliptic. The moon, which is the main thrust of what we're talking of what we need to relate to the sun, also moves roughly along the ecliptic. But anyway, for the time being, let's
What is the Rambam call it?
what?
What is the Rambam call it?
Well,
Muscle.
huh?
Muscle?
No, not exactly. Okay, the Rambam uses various terminology. All right, now, okay. When he was going around the Earth, he was going around the Earth at a constant speed, right? A certain number of degrees per day. We said it was a lot, but very close to a little bit less than 1 degree a day. Constant speed. Constant speed means you don't change your speed. Every day it's the same amount. So you can use rate times time equals distance to determine where it is along that constant speed path. Very simple. Constant speed that Rambam calls in various contexts hiluch soy. And soy means a circle, something going along a circle at a constant speed. It sounds like it means average, but and it is in fact an average, but it means something very specific in the context of how the Rambam learns and teaches Kiddush Hachodesh